Yeah, for those of you who don't know me, I'm Florian. I'm heading the Applied Geophysics group at the Montana Universität Leoben. That's a small town about 150 kilometers from here in Styria. And it's kind of a mining university. And so I'm a controlled source seismologist. So I don't really have much experience, field experience from, so my EM knowledge is totally from textbooks, but we do some on the side. We do some DC stuff, we do some GPR stuff, GPR straightforward because it's close to seismics. At Leoben we are 5 faculty and 3 staff. Yeah, that's about it. Our group is like, with PhD students, we're I think 10 or 12 people at the moment. So I'm showing some DC ERT work that I've done along the way, and I can actually, this was work in the Salzach Valley. It is a combination of GPR and DC resistivity. We did that for classical hydrogeology characterization. It was Austrian Power Grid wanted to build a running power plant in the river, so they wanted to know the aquifer structure so that the water doesn't come into the cellars of the people. And actually, this was taken as a ground truth because we were doing refraction seismic and full waveform inversion to see the aquifer here in seismics. But I haven't, and we do see it in seismics, but I haven't brought it because, well, I thought it's not interesting. Well, anyway, so this is some of the work we're doing. That's a pole-pole survey. Oh yeah, so archaeoprospection, that's a pole-pole survey, trying to delineate here. Well, the work didn't proceed to fill out all this, but somewhere here is a Roman building that we wanted to detect. This is GPR now through a castle yard that is classical lines detection, cables detection, but also a tunnel is what we were actually looking for here. In the, 2 meters, 2 meter steps. So that is some of the work we're doing. Here's another archaeoprospection that we've been doing with radar here in Salzburg, here in Styria, at various scales. We have been now working with Strabag. That's a more complex topic. It's a mass movement that we want to monitor. So this is the baseline ERT that we have been doing here. We have been doing more ERTs, but yeah, and I think one of our problem was that the precipitation was extreme. We did this year, and there was almost no precipitation. So, and we wanted to see if they have drainages actually here at the several positions. They have built drainages, and we wanted to see how efficient they are in taking the water out. And here the whole slope is moving actually, so this is it's a moraine deposits, and here that's a diabase that they are mining here to make gravel for the train, or for the railways. Yeah, and then there's a geophysical, geotechnical work. And so this is time lapse, but so far we have, because we don't have much experience here, what we've done is simply inverting. What the student did, I have to say, is simply inverting every model. So I don't think that is the way to go, and we will have to continue to work on that. But on the other hand, the problem was really the very, very little rainfall that we had in the period also. So that's probably the signal that we have is insignificant.
So again, what is it that you might have hoped to have found? Like if you had rainfall, then you'd have some conductive?
Yes, that's like to see conductivity that increases, so that tells us where the water comes in, but at the same time see that it doesn't stay somewhere. Yeah. The bedrock structure is often, it's a very steep topography, as you can see, and the bedrock structure often is in steps, and so then the water would stay in here and destabilize the whole thing. So that's, and they have drainages in here, and we wanted to see how fast that removes actually the water. And actually the monitoring is still in place, so it's ongoing. We can go there. We plan to go there and take data, but this particular student left, so we have to do it. We have to do it on our own.
But that means you have all of the the probes that are they're just sitting there.
They're just sitting there,
and you just have to hook them up.
Yeah. Yeah, we left the probes in there. We took, and we have some that we could spare that are actually, I think, 3/4 of a meter long, so we really get them even.
Well, and there's the potential for rain to come, I guess. So.
Yeah. Yeah, so here we don't have much experience. I don't know, maybe we can share some experience about the software that we have to do something else than just invert them separately. But yeah, and the next thing is that, so more interesting to me is a radar, and actually the next thing that we are planning is a cooperation with Omnia to use the radar subsurface for roof stability. So we're going to do some, there is a cooperation agreement already. At the moment I'm looking for someone who does, student who will do that. Yeah.
So I just wanted to say that in the normal REST-GP inversion result, you don't see the changes, even if. So actually, therefore we've got this program developed with Jang Ho Kim, who was here several years, each year some months here. The program is quite complicated to learn or to use. But our data, which we have from several sites, you just don't see it in estimate. The inversions you show, it just doesn't say that there's a difference there.
I mean, these are different models, and they do show differences, but I have to say that because it's a nonlinear inversion, I don't believe in the tiny differences here. Yeah, so
you won't see it, I tell you that.
Huh?
You won't see it.
I'm seeing differences, but
yes,
I'm
but
asking if this is something
just
meaningful. Yeah.
Yeah.
Yeah,
that can be also due to different. Yeah. You have inversion results from other sites where you see nothing with the channel program because there's not so much to see, and you might want to see something in these results. We also have results like this, but they're not significant.
Sorry, do you mean that when you do the inversion on sort of a time-lapse survey, you don't see the results after inversion?
No.
Okay, why is that? Is it just too small of a difference?
It's you can be lucky if you see 10%.
So it just falls within the error of the inversion, does it?
No, the error is 6% is nice.
Typically, I think what the reasonable thing to do is that you form really the differences in the data.
Yeah.
And because if you invert a data set, it's a nonlinear procedure, there's a big uncertainty in the model. And small differences in the data can make large differences in the model that may not be realistic, is what she's saying, and what I also believe is happening here.
Well, maybe we can do
And
some
I
kind
think
of
that we should
cooperation.
somehow form the data differences and invert these, but I don't know. I don't have a code to invert the differences proper. And I mean, you need some background model to invert the differences, to project them somehow. Yeah, that is maybe just to show what we are.
Yeah, that's great.
Can I ask a question, not exactly on your topic, but just in general? You're talking about rainwater. I'm wondering, Doug, how does this ground saturation affect each of the different methods? Are they all better with some water in the ground or none, or do some of them work, or like how does that?
Better or worse, so you're going to become more conductive, that generally when it's saturated. From the point of view of trying to detect if there's something underneath, at depth that you were trying to detect, as long as you can get current into the earth, then I don't think it's such a big deal.
Okay.
Who else would like to present? There were a couple.
But I have just an application of sustainability measures in agriculture.
Oh, that'd be great. Yeah, sure. Yeah, come on. And it's you can.
Yeah, I don't mind. I don't have to either. I'm fine. I know we're.
Talk about a project that was done in the area of Canuto, and we wanted to explore the region of a wine growing area, and all our colleagues that are mentioned here work together in the field of climate, soil and geology and geophysics and geochemistry. And the project aimed to explore the viticultural function of the region, because the wine growers wanted to know how their soils, how the property of their soils would affect the wine growing. Yes.
So that's interesting. So you have a project that involves wine, and you get so many people that are getting on board.
Yes.
Yeah, like it's amazing. You try to do that for something else, and then nobody comes. But here now, everybody wants to participate. Wow, well, that sounds like a really good thing.
Of course, it's only because it's the wine, I know, but it's also the thematic interaction of different disciplines, and so the study was done in a 3-year period, and we wanted to capture the major parameters and properties of this area for the agriculture and viticulture functions. And we gathered various thematic layers and tried to put this together and integrate this in a combined way in a geographic information system. And to hand our results over to the wine growers and their consultants, we also put all our maps and results in a web map application. I want to show you where this project took place. We are here in Vienna, and this is the area of Carnuntum in the eastern part, below the river Danube and also south of the river Danube and north of the lake Neusiedl. And these are the areas where the climatic conditions allow for wine growing in Austria, because they are preferable warm climate conditions in Austria. And the area of Carnuntum is on the eastern part of this rim. And this is a Roman monument where this, because this area is also very famous for the Roman remnants of the Roman culture, because there was a huge military town of the Romans here. And this is what the landscape looks like, you know, with the culture. It's not very easy for geologists or soil scientists to gather information, because you have a lot of vegetation and not so much outcrops here. And we did, the colleagues of this project team did some climate observation, microclimatic conditions were measured, and they did also some modeling of this area. The soil scientists took the samples and interpreted the soil maps, and we made a detailed geological map of this area, and took also samples which have been analyzed in our laboratory for geochemistry and mineralogical contents. And of course, geophysics, last but not least, was a very valuable tool, because as you've seen the landscape, it's not easy for the geologists, and the geology of this area consisted mainly of soft rocks, silts and claystones and sands and gravels, and also some carbonate. And it varied in a very small scale. So the wine growers have been interested in the variation in their own plots. So even a map of 1 to 10,000, it hasn't been sufficient to capture all this variability within their wine growing region. And so we, fortunately, we got some resistivity maps. It was done by a French company, GeoSci.xyz, and also resistivity profiles of our colleagues of the Geological Survey. And you see here, for example, it's very small here in this resistivity map, and there has been a profile, and you see here that the morphology allows here for values of lower resistivity and down here. So there's a lot of erosion going on the hill slope, and the soil build-up is mainly concentrated downside of the hill slope where it's accumulated, and also on the top where the morphology is allowing the build-up of the soil. This is one example. And the other one is the generation of the resistivity maps. This is a device where the quad taus the instrument of the geophysics, and all these spikes are the poles, and they get similar to the airborne geophysics, they get lines, because in the viticulture, you know, the plants are also ordered in line, and they get on the line they get a resolution of 10 centimeters. But between the line, it depends on the orientation of the plants. and they capture the position with real-time GPS, and it's a very shallow geophysics, just about 2 meters, and they make the grid, the data, and they make three maps, integrated variant resistivity 0 to 50 centimeters to 1 centimeter and about 2 meters. But that is the target depth for the vine growers, where the roots of the plants are situated. Yes. And so these are you see here the plots of the vine growers, the estates, the property of the vine growers, and these parcels have been measured because these vine growers were part of the project. And these are the voids, because these people didn't attend our project. This is interpolated. I think it's the shallowest part, 0 to 50 centimeters. Yes, it was done by GeoSci.xyz, and they call it automatic resistivity profiling. They go with about 20 kilometers per hour through the vineyards, and in agriculture this device is now common practice. They call it precision farming or precision viticulture, and the vine growers, they see, for example, here there are more gravelly soils, and here there are more clay soils, so it makes a difference for the plants, for the water status, and so they know how to treat the plants. Or there's a difference when should they harvest, where is the fruit, the perfect date, because it's there, it's ripe, and they're not. And also for irrigation purposes or for applying fertilizers and so on. They were very happy with this.
Oh, that's
and we also
great.
do, because of these maps, we didn't know where to go and take our probes, because it looks a lot less sophisticated than the devices before, but it proved very, very useful. Well, and afterwards we made all our GS layers out of these datasets and put it by the help of colleagues of our IT and geoinformatics department on the server of the survey, and so the vine growers and their consultants can take our maps into the field with their mobile devices and decide what to do if they plant a new vineyard and choose the correct amount of fruit stocks and different varieties and so on. They can use also some transparency, so they can see through the geophysics maps and identify their parcel and so on.
So would those images then be live then on the web? Anybody could get them?
We have it on our on the homepage of our survey. Yeah. So that's for now a very short presentation, but
that's great.
It's a very interesting project, and geophysics we were very happy to have these results in our maps. Yes.
But see, here's another connection that you have with geophysics, with the average guy on the street, right? He wants to drink good wine, and here's a way of getting some information about the soil and how to really manage your crop. I mean, people resonate with things like that.
It was also a challenge to communicate this technology and this science to the local wine growers. Yeah. They didn't hear anything about this before, but in France and in Spain and so the huge winemakers, they have a lot of technology and they do also the remote sensing and all kinds of stuff. And so.
So have you noticed that some of the places that were blank, where farmers hadn't signed on, are now looking at this and say, hey, wait a minute, you know, I'd like to have that information in my place too?
Yes, maybe, but they have to contract the company for themselves. Because this was a very active progressive group of winemakers, and they gathered together and paid the scientific team also, because also with funding of the European Union and federal and local governments, but they also paid for the study and also for the geophysical survey. Yes.
That's great.
Okay,
Thank you.
Thank you.
Thank you.
Did you taste the wine before and after?
You see? No, he didn't, but he did bring a free bottle to everybody who attended this. I'm sure you did.
Sure. I'll try to go. Is that mine there did too?
Yes.
Okay. So I'm also going to talk about more of an sort of application, sort of technology side of it. I don't really have a question to ask, but I thought I'd share it anyway. So I work for a software company called GeoSci.xyz. We usually specialize in gravity and magnetic data, but these are the areas that we've kind of forayed into the EM and the electrical methods. So we've got some IP. We've recently come out with a 3D IP inversion. We've got frequency domain 3D or pseudo 3D inversion. But I'm not going to talk about those right now. I want to talk about actually the UXOs that we've got here. So I've broken these up into two categories because one of them is a lot more interesting than the other one. So traditionally for land-based UXO surveys, a lot of people are using sort of an EM61 sort of instrument, which looks like a lawnmower and has 3 or 4 time gates. So you can get a little bit of information on the depth of the target. You get a little bit of a decay curve, but there's not a whole lot that you can actually get out of that information. So we've got sort of a software package that lets you process and interpret as much as possible from that data set. And that's what a lot of people outside of North America have been using, although maybe Australia has something that we were talking about earlier. This one down here, the second one for the time domain, is something that we've been working with the American Department of Defense for the last 15, 20 years, something like that, developing a really powerful new system. So we worked with them and an instrument company called Geometrics that was developing this new system called the Metal Mapper. And the survey has the traditional dynamic survey where you can push your card around, collect some data, find where your targets are, and do a little bit of interpretation. It's got more, I can't remember, about 20 or 21 time gates. So you've already got a lot more information to get some better depth estimates, to do some very sort of rough classification. But the real benefit comes in from a static survey. So the surveys are broken into 2. You go around, collect your data, get a list of targets, and then you go back out to the field and you actually park the instrument over top of it for 30 seconds or a minute, something like that, and collect a huge amount of data where we've got 122 targets. So that's where things can get really interesting. I've already talked about that. One of the downfalls of the original method, which, like I said, has been used in a lot of places already, is not only that you can't get a lot of depth information, but that up here, for instance, we've actually got 3 targets that look like completely different objects, but they're actually exactly the same object. You probably can't see it there, but they're just in different orientations. So you've got a long cylindrical munition oriented in different ways. It looks like completely different targets. So if you're not sure, you either miss it, which could be dangerous, or you dig it up when you don't need to, because you don't realize it's actually the same object. So this is sort of a cost breakdown that the US did for the distribution of their costs. And digging up scrap metal was by far the largest cost that they had. So if you've got dangerous objects in the ground, you obviously need to dig them up. But if you've got scrap metal, you don't want to waste your resources doing that. So the software package that we developed, along with GeoSci.xyz and the Department of Defense, was to come up with a really powerful classification tool that would not only let you know whether or not something was scrap or munition, but it could actually even tell you what type of munition specifically you were looking at. So you could decide yourself whether or not you're interested in it. So they created sort of a prototype, and now they've got one actually that is commercial. And this is the setup here. You've got multi-axis coils or single plane. These are them 2 here. So we've basically got, actually, we'll go to the next one. This here where we've got inside the instrument, you've got 4 transmitters, and inside each of those blocks, you got a receiver that's actually measuring all 3 components of the electromagnetic field, X, Y, and Z. And so for each of these sections of the instrument, you actually get decay curves. You actually get 12 decay curves. From that, we can actually get some information on the polarization of the object itself, which is intrinsic to that specific object. So every shape is going to have its own polarizability. So we can look at sort of the width, the depth, and the height, which can help really specifically characterize the different munitions that you've got. So here we go. So you take all 4 of the transmitters, all of the receivers, combine them together, and you get a polarizability plot like this, which has all 3 components of it. I don't know if I took the slide out. Yeah, I took the slide out. Anyway, yeah, so you basically get those 3 different curves, which can help you. You can also get information on the slope of the curve and where they are in relation to each other as well. You can get very precise location of where the object is underneath your instrument, because depending on which coil it's closer to, it's going to be able to get a higher signal and be able to sort of implement that. I think we're down sub-centimeter sort of accuracy into this. Just showing it sort of how the plots change as you just move the location around a little bit. Oh, there it is, okay. So the different decay rate, relative magnitudes, and total magnitudes. There we go, okay. So once we've got the polarizability curves, we can start to compare them from one object to the next. So what you actually do is you actually build up a library for these items. So you can do that in really clean conditions by taking an object, putting it below your sensor, and creating these curves yourself, and just building your own library. And you can see how different the 2 curves are here for a horseshoe and a small munition. It doesn't have to be objects that are that different, though. This is an example here where you've got exactly the same 37mm projection that was kind of changed over several years, where we've got a metallic band here at the far end, here at the front, and here it's fallen off somehow. And the polarizability curves are different enough that you can actually distinguish. We know it's that type of munition, but we know it's not exactly the same. So that's the kind of accuracy that you can get from this type of technology. The idea is once you've gone over your survey, you've been able to classify based on your library, and you can break yourself down into a dig and no dig to determine where you need to go back to. So the green is safe, we can leave it in the ground. The red is something that's come up in your library that you've identified as a munition that definitely needs to be dug up. And the yellow is where you found something that doesn't match your library. The interesting thing is though, is you can go back to any of the objects in that yellow section, dig them up, determine what it is. Once you know what it is, you can add it to your library and you just rerun the classification, and anything else that matches that will be put into one of your two categories. So it's quite easy to sort of continue to build up the library as you go. And the idea is eventually you get the dig list on the right there where you have a dig and a no dig. Now there's a lot more details on how they do that. They do dig up a certain amount of the green ones as well to just give sort of certainty and for health and safety reasons and that kind of stuff. But I could go on for an hour about this, so I'm keeping it simple. So that's the basic idea of that new system. So up until this year, that was only available in the US because of patent laws. That's now been opened up to the rest of the world. So we're hoping to kind of get some traction of that in Europe, because right now all we've got are those sort of more basic EM61 type instruments that people have been using. So we're hoping to get a bit of traction over here. Obviously the libraries would be very different because of the types of munitions, but like I said, it's pretty easy to build it up. So we're hoping that could be kind of useful for people here as well. We do find a lot of bombs. As far as the future, where we're going with this, that was all land-based stuff. We've actually got, I don't know how much you guys interact with it, but a lot of, well, several European countries anyway are doing a lot of marine surveys for UXOs. And the primary tool right now is magnetic data. So they're towing gradients. But there's a couple of problems with that. First of all, there's intrinsic problems with magnetic data with how much you can actually extract from that as far as depth is concerned and as far as differentiating different objects. But one of the other big issues is that there is at least one type of bomb that we know of. I think it's a German-made aluminum bomb that was specifically made so it's not detectable by magnetics. So that makes it really difficult. You can do a survey and say there's no bombs here, with the caveat that there might be loads of this other type of bomb. So EM is starting to move into the marine world in this industry. We've seen a few instruments come out, but that are very black box, and the results have been a bit uncertain right now, sort of how sort of accurate they are. Geometrics is planning on building a system just like this one for the marine environment, but it's currently in development at the moment. There's a lot of issues with the type of accuracy that we need to get for UXOs, which is a lot more than we need for geology usually. That sensor needs to be super close to the bottom of the sea, and then you run into actual practical problems of how you do that, and so you probably end up having to put that on an ROV or an AUV, which increases the costs again. And so there's going to be some questions as to sort of how practical something like this is. There's obviously a lot of potential use academically, but whether or not that could help in the industry, whether or not it would just be too expensive. So as that develops, we'll probably be involved on the software side as they're developing the instruments. So that's sort of a long-term plan, but just a bit of an update on different industry, I guess, that a lot of you guys are working on. So yeah, that's everything.
Great. Thanks, Sarah. Yeah, as I was saying earlier, we had thought before we came to Europe that, well, actually, and the same occurred in Japan and Korea. So we thought, okay, these places have all had the heck bombed out of them. So there must be tons of ordnance items and it must be a big problem. But we went to Japan, we went to Korea, to Netherlands, and asked, oh, is anybody interested in UXO? And boy, the interest has been completely underwhelming, so it's interesting.
I think it's probably there, but probably more in MAG than in EM. But there's more and more coming. It's been interesting. We've had, as far as sort of the number of clients that we have, marine overtakes land significantly. I'm not exactly sure why. Obviously, there's a lot in both places. I'm not exactly sure why. I know I was in Singapore recently for UXO work as well, and they were doing EM, and I was kind of asking as well about why we haven't seen more of that, and they said that they just tend to not have the money, perhaps. So they're doing surveys, but they're just more sort of basic, rudimentary instruments. So they're not necessarily doing advanced processing and classification, maybe more like a metal detector or something at that level. So I don't know if some of that might be why, at least in Southeast Asia, Europe is.
I think it's, for example, it's the geological survey phosphate, we don't have an insurance. I think it's an insurance reason. Because of course we have the instruments, not this one, but we've got magnetometers and so on. And we did already have the question, can you search for bombs? No, we do not, because we do not have an insurance. Who says if you detect one or do not detect one? So maybe not the right companies have been addressed here.
I don't know.
There are companies in Austria which really do that as a main task. And I think they're not sitting here.
Yeah, I was going to say some of the European countries, and I don't know them all, but some of them have sort of, because of those reasons, have put them entirely into the military category. And in fact, a lot of our clients are companies that are sort of ex-military personnel, bomb disposal experts, and those sort of people that come from that industry. But a lot of, like the Netherlands, I think, are now open, but for a long time it was all in the military, and so they had their own people and doing their own things because of what you're saying. Yeah, so it's even now with our software, when we look at bombs, people want us to put out standards to say, yes, we can conclusively say this is dangerous or not, and we can't.
Yeah.
As far as the software, as far as the data.
I don't think that any director from, let's say, research institute will say, okay, that's a fault, okay,
exactly.
I'll take it.
And this is where we're wondering if we're going to see a change in the next few years with this new technology, because this was built up with the US government. And that's why they wanted to have control. And so they have really, really, really rigorous standards. All of their processors that work on these have to go through training courses and actually pass the test. There's like, they've got a field site outside, and they have to do the survey, process the data, and correctly identify all of the bombs.
And you have to be liable.
Exactly, and then you have to be liable for it. And so they've got the whole thing set up, where the processing software is just one small part of that whole project that they've got. But that's, I think, what they're hoping, because right now we don't have the technology to give you the accuracy that you need. But with this new technology that actually does give you that sort of accuracy, so we may see a shift when this is available.
For example, I don't know how it's working in areas like Pennsylvania. Developed and rail tracks out there. So,
I'm sorry.
How is this working in densely populated areas? Towns, railroads behind there. So.
Last night they found the bomb near my flat.
Yeah.
Oh, really? Oh, yeah.
An American one.
An American one, okay. At least it wasn't Canadian one.
Yeah.
Yeah, I think there's obviously some issue. I mean, I have seen surveys in populated areas, but they're obviously going to have interference and.
No, I think the most white people are not. It's a liability.
Yeah.
So.
I think this is an interesting discussion, but I think we really should move on and hear a little bit about SIMPIG.
Yeah, well, thanks to everyone who presented. It's very interesting for us to get a perspective on what's going on everywhere, what types of problems people are working on. And I'll start by showing you a few of the resources we've been developing. I also want to show you what we're doing with the blog and what we've done in other cities with content that has been shown to us on the second day of the course. Yeah, so let's start. So the main set of resources that we've developed, and like the main portal to our resources, are through GeoSci.xyz. And so if you go there, you'll see a page that looks like this. So there's a few different things on here. There's the GPG, and this is really an introductory style web-based textbook. It's Geophysics for Practicing Geoscientists. And we've used this in an undergraduate geophysics course at UBC. And the course is taken mostly by geology and engineering students. So this is really meant to be like a once-over lightly on all the geophysical methods. And it's again like an open source resource meant to be growing and edited and all of that. So you're most welcome to jump in and contribute there. EM is the one that's been developed for this course specifically. I'll jump back to that in a second. And then the other thing that I want to show you is SimPeg. And so SimPeg is the open source software for simulation and parameter estimation in geophysics that we've been developing as a group. Really started at UBC, but has since grown out, and we've got contributors at a number of other different universities in the States and across Canada. And so we're hoping to have this grow and be a resource that can be used to simulate and invert really any type of geophysical data. And I'll show you an example of how we're using SimPeg in EM GeoSci. So EM GeoSci, this is the main like textbook resource that we've developed for the disc on electromagnetics. And we've got a whole bunch of different pages that you can go and peruse and have a look at. Some you will come across that'll say they're under construction. So there's pieces that are still growing and absolutely open to contribution. Two that you might want to check out, there are the case histories. So this is the collection of examples that are put into a 7-step framework where you can work through and see what kind of applications of EM have been used. Each one, as I said, is in this 7-step framework, and for most of them, there is actually like a published paper that it is based on. So you can go into the paper and see like all of the details, and then what's on the web is really meant to be sort of a synopsis and a bit of an overview. And so if there is a case history that you'd like to contribute and have added onto the site, we want this to be a growing part of the site. And the best way to do that, if you have an example, is to first just get in touch with us. We're hoping at some point to streamline like getting content onto the web. But right now there's a few steps, so it's best to first get in touch and then we can help you make that happen. The other thing that I want to show you is the apps. So if you go here, this is probably the first way you'll access the apps. And we've got two styles. So there's the EM apps, and that's what you would have seen yesterday. So those are really simulations that are hooked up to slide bars and toggle buttons and widgets. So you're not really seeing much code. It's very much targeted at like immediate interaction and examining the physics. The other style here are these simulation notebooks. So there's less of these, but what they're meant to do is actually expose all of the code. So these are examples that will walk through step by step how to actually set up and run a simulation and an inversion using SimPeg. And so I'll show you an example of one of those. Let's start with the EM apps. So there's a couple ways you can access them. If you're familiar with installing Python and using Git and GitHub, you can download it on GitHub. But what I would recommend is that you use Microsoft Azure. So if we go here, this takes us to a Microsoft service where they actually can run Jupyter notebooks live on the web. And so this is what this library looks like. And right now you'll see that the run button is grayed out. Is that okay? So that just means we're not logged in right now. You have to be logged in order to access all of this. It's free to set up an account. So you can sign in, and if you don't have an account, there'll be like the sign up button. So you can go ahead and do that. And so now that we're signed in, we can go ahead and actually make a copy of this library. So this is kind of nice, is what actually happens is you'll have your own copy that's stored for you. So if you want to go in and make notes and change stuff, that'll persist. So that'll be saved to your account. So we'll clone this, which is just making a copy. And this pops up just because we've already cloned it to Doug's, so we can go ahead and overwrite that if we want. And now when we click on an example So the one we saw yesterday was this DC cylinder. We fire up a server somewhere, and then we get into the Jupyter notebook. Once you're here, there's two ways you can interact with the code. So you can run it cell by cell. And what that means is just like this chunk is like 2 lines of code, so we can run it cell by cell, each chunk of code. And you can do that by pressing Shift-Enter. The other thing that you can do, see this cell button? You can just do cell run all. And that's the easiest thing for all of the apps, is it's meant to just be run in 3 different steps. You know, we install the packages that you need, then we import them all, and then we'll display the app. So we'll give that a second. And so the packages that this is installing right now, there's one called EM examples. And this is a collection of scripts that our group has written basically to build all of these figures. And all of those scripts are based on SymPeg, which is that open source software. So once you've gone and run them all, then you can actually see the images and the widgets pop up. So you can go ahead and build your model and then look at the currents and the potentials and results and things like that. So with each of these style of apps, we've really kind of fixed the set of parameters that you can play with. That's the easiest way to actually go ahead and make something interactive, is putting some constraints on it. But in a lot of cases, you really want to be able to play with and set up your own models and things like that. So if we're going to do that, then you want to look at these simulation notebooks. So if we go here, this also has an Azure link. So this is the one that you want to follow. So we go ahead and go there. And we'll make a copy of this as well. And so there's a collection of notebooks here. So there's about a dozen. With the EM apps, I think we're up to 25 or 26. So you can go ahead and flip through those, because there's some for DC, there's some for frequency domain, time domain, etc. These ones, there's just a handful at the moment. There's a DC example. There's a couple frequency domain examples. And then there's a set of MT tutorials. So this is targeted really at exploring some fundamentals of inversion. There's a leading edge short article that accompanies this. So you can go through and work through each of these if you're interested. The one that I'm going to show you right now is there's a time domain vertical magnetic dipole sounding over a sphere. And I'm going to blow through this pretty quickly, but if you do have questions, we can chat about that afterwards through Slack or email or anything. And so these ones are ones that I would recommend you run just cell at a time. It's meant to be something that you walk through, not just get to the end. So in this case, all we're going to do is install SymPeg, and then import some standard Python packages. So if you're familiar with Python, you'll have seen NumPy, which does all the matrix calculations. So it's basically like MATLAB. Matplotlib does plotting, and then SciPy has a whole bunch of scientific resources. So they've got some stuff for optimization, they've got some stuff for sparse linear algebra, and then this we're just using some constants. And then from SymPeg, we import different packages that do the meshing. There's some utilities, the time domain code, and then some solvers. So in this example, what we're going to do is build up a model with a sphere in a half space, and then we'll do a time domain sounding. So we're going to have a transmitter above the sphere, so we'll put it 20 meters above the surface, and put our receiver 8 meters offset, and define some times to look at. We go into some things looking at diffusion distances, so we make sure that we design an appropriate mesh so that your smallest cells are fine enough to capture those quickly varying things, and then make sure that basically our latest times, our mesh goes far enough so that the fields have decayed. So that's all we're talking about here. So we go ahead and set up an appropriate mesh, and then we can plot it and make sure that it's satisfying our assumptions, that it's going far enough. And then once we've set up all the parameters, we can go ahead and put the model on the mesh and have a look at it there. And then go through and define a survey. And plot out results. So in this case, this one shows you can go ahead and look through time at dB/dt as we go through time. So that's just one very quick example that you can look at to get up and running a bit with SimPeg. The other thing that I want to show you is some resources on SimPeg and also how to get in touch with us. Because it is, anytime you're learning new software, it's important to be able to contact a person. And so, sorry, I'll start from GeoSci again. So if we go to the SimPeg site here, there's a few things to take note of. There's a paper that is in Computers and Geosciences that gives you a bit of an overview of what we're thinking in terms of structure and how it's laid out and organized. The documentation is a good place to start, so we'll go there. And this is the piece that's worth paying attention to here, is we have a Google group. This is a forum. And so this is really a place where you can email, get in touch with people. So this will go to all of the developers as well as people who are using SimPeg. So if you've got a basic question of, I've got a 4-layer model and I want to do a frequency domain sounding, how do I start to set that up? We can then point you to the right handful of examples that'll get you moving. So that's how to get in touch. In terms of where to actually start in the documentation, you can dive into all of these specifics. I would suggest starting at the examples, and just that gets you through, gives you something visual and an immediate application. And the way that these are organized is we've got a handful that have been published. So if you want to reproduce something from one of the papers that we've highlighted here, you can. These are perhaps a little more involved than a starting example. In a lot of cases, we're doing a lot with the plotting code and things like that that is really inconsequential, but you need it to make it look nice for publication. So I would instead suggest starting with some of these. There's examples showing a linear inverse problem. So this is a very basic example. And then this one here shows if you'd like to play around with things like compact norms and changing the norm. What does that do in the inversion? There's some examples that show how to build up a mesh. And then there are application-specific examples. So gravity, magnetics, DC resistivity, there's frequency domain EM, there's a natural source EM example, so like magnetotellurics, time domain electromagnetics, and then there are some fluid flow examples with Richard's equations, as well as some very basic straight ray for seismic. Seismic is not really been developed all that much within SimPeg yet. Our group is mostly focused on electromagnetics and potential fields, so there's lots of room for contribution there. So that's a very quick overview. Are there specific questions or things that you would like to see? Yeah, anything? Hopefully enough to get started, and at least there's a few resources and a way to get in touch with somebody. So
Looks really awesome.
My side. I'm mostly interested in how the forward modeling exactly works, but that is, I guess, beyond the.
For this, it's all finite volume based forward modeling. There's a few details in the SimPeg paper if you'd like to check that out. But yeah, it's all finite volume.
Finite volume.
Yeah.
So would that compare with ComSolver?
Yes, we've run a handful of comparisons with ComSolve results for the frequency domain electromagnetics and for.
But it is open source.
This is all open source.
Okay.
Yeah. Yeah. yeah, and the code is all up on GitHub, and you can download it, look at it, fix things. Perfect. Oh, the one last thing that I did want to show you is the blog. So if we go to GeoSci.xyz, the disk button here, this has all the disk-related items. And there's a link here to the blog. And so you can see and have a look at each of the places that we've been so far. We tend to lag a few weeks between the event and getting it up, but you can see what's gone on at each location. See if this comes up. So what we've done is we'll provide a bit of a summary of the audience, who was there. We'll go through one example of some of the presentation material, as well as generally a case history. And then the part that I did want to show, and just make sure that everybody who presented, if you're comfortable with this is what we'll do, is we've put just a photo as well as a link to the presentation and a quick summary of what people discussed. So we'd love to do that here. That helps highlight what's gone on at every location. But again, if you'd prefer not, then just let us know and we won't post your material with it. So yeah, but what's nice about this is then you can go ahead and actually see what happened in Australia, for example, and see if there's some overlaps with what you've been doing. So,
So all of this at this point is just meant to be a portal and raise the awareness that, oh, at least this stuff exists. And then you take a look at it, and then there's ways to get in touch and communicate. But unless you know that the stuff even exists and it's completely invisible.
okay, perfect.
First, I want to thank everybody for, especially for the presentations. That was really great. Those were good presentations, and really, I really appreciated the audience. And interested, engaged, and yeah, that makes us. It just makes it feel more worthwhile from our perspective. We put in a lot of effort, and our goal is to try to be effective and make an impact. And if we do have an audience that really is genuinely serious and interested, it's a huge difference. So yeah, thank you everybody for coming out. We hope to see you on the web. Connections.
Yeah.
What questions were you?
Oh, yeah.
Just we need to be clear by 22.
What's your question?
No,
Ich glaube jetzt nicht, dass es
I took
speziell
neither. Okay. I think it's probably more than an 8
Wenn ich-
That's fine. I'll see if I can find one.
Well, feel free to email as well.
Okay. It was just clarification.
Oh, we're just going to, we'll ask him while we'll.
Let me just double check that.
Und das wird jede Übersetzungsprogramm.
Ja, deswegen ist die Programm